Let me introduce our next speaker. It's Yasha Bubnov from Juna, and his talk about concurrency architecture patterns. Yes, something like that. Thank you.
Doesn't work anyway. So hello everyone. Do you hear me? Yeah. Do you hear me well? Okay. So please tell me, how much of you came here using Uber? Okay. Not much, right? And how much of you came here using Juna? Yeah, that's a problem. So it works only in New York right now. But despite of that, I know that at least one of you will leave this conference with a ticket, with a present from Juna. Back again. So the present is simple. It's a ticket to the Skolkovo conference, which will be in 2018 in November. So the best question will get this ticket, a part of the Tshirt from the conference. All right? Okay. So let's talk about the the concurrent server architectures. So late in the 1999, Dan Kegel posted the white paper. So he said that it's time actually for what the hell was wrong with that? So he said that it's time for programs to actually handle at least 10,000 connections. You probably hear that back again. Okay, thank you. So he proposed several solutions to the problem of handling 10,000 client connections. One of them is handling them using the customized kernel. Basically, he proposed to write a server which is running in a Linux kernel. Well, the problem with that each application you are going to write requires a custom kernel. That's probably not another good way of doing that because it requires time. And there are two more solutions. The first one is handling, both of them relates to how to handle the clients, many clients in a single thread. The first approach assumes using non-blocking input-output. And the second one assumes using the asynchronous input-output. Further, we will discuss how he came up with these ideas and why these types of handling client connections is so efficient. So let's start from the old school theory. So the first approach of writing servers is just writing in a sequential way. So every time the client the server would like to handle client connections, it creates a socket, reads requests from the client, then writes responses back to it, then closes connection, and that's it. That's it for a single client. All other clients have to wait for that. The Go implementation is pretty straightforward. If you ever tried to write TCP server, I mean sequential TCP server. So this assumes only just creating a listener socket, accepting a new client connection, and just handling requests sequentially until the client is done with their requests. The problem with that, as I said, the only single client could be handled by the server. The rest of them should wait until the first one is done. Well, the solution is pretty straightforward. We need to somehow handle them concurrently. And the scheme of such server differs only in one thing. It means just to handle them concurrently. The first approach of making this working is to create a clone of the process. So whenever a new client would like to connect to the server or communicate with that, he creates a fork or a clone of the process, and that means that a new process simply handles the second client. That approach works, but the memory footprint of the process is quite large, and therefore we could try to use something more lightweight, and this is thread. So the scheme is the same, but we're just using threads. That works as well, but there is also a disadvantage of such approach. Whenever the amount of clients increases, amount of processes to handle them also increases. And with the limited amount of resources, we are running out of memory, running out of CPU, so our Linux machine, which is running the server, can handle even that client connections that are already connected. The solution for this is to create a fixed amount of clients, a fixed amount of processes or threads, and make it sleep, make it wait until the new connection arrives. That is good, actually. But what happens if new client is connected? That actually, talking about the TCP stack, every connected client is going to be is presented using a queue. So every client goes to that queue, and when a process is listening for new connections, he is subscribing to events on that queue. That means every process that is listening will be awakened by a new client. And there is a problem called thundering herd, which relates to how much processes, which means that all of the processes that are listening for incoming connections will be awakened. They consume all of the CPU because they are fighting for a resource, and that resource is a new client connection. The solution is to use a mutual exclusion for that. It means whenever a new process would like to accept a new client, he is trying to, at first, lock the file mutex. Only one process locks it. All of the processes are just listening, just waiting until that process accepts a new connection. Similar approach with threads, but as I said previously, as long as they share in the same memory, we could resolve this by just using semaphores or in memory mutexes. But well, how it can be done in a Go language? We probably would like to implement that, but well, there's a problem with that. The standard library that provides an interface for most of the system calls just doesn't provide to us an interface to create a fork of the process. It simply creates a new process and immediately after that replaces with a new program. That is all we had. That is all we have. And that approach, that solutions are not applied to the Go language. And it is very important to emphasize that. It is a very important thing because Go language doesn't allow us to do the wrong things. And it defines the new approach, how to make the processing right. And it could be done right by using user threads. It's a way of using only a single thread for handling a whole lot of the whole collection of the client connections. But well, talking about the Linux, we could just think about how it could be implemented in Linux, how we could implement the user threads. So there are 4 combinations of the words blocking, non-blocking, asynchronous, and synchronous. And therefore there are, and they are represented by different system calls. So the first approach is using blocking synchronous input-output. That is probably the simplest one and the most inefficient one as well. This blocking synchronous I/O represented in Linux using select and poll system calls. They require at least they depend. The time of processing client connections depends linearly from the amount of connections we have. And by the way, the select system call is limited by the approximately 1,000 client connections to be handled at once. So that doesn't help us to resolve our problem. And there is a better solution of using the system call epoll, which is allowing us to understand what of the listening, what of the clients are now ready for processing in a fixed amount of time. And by the way, it allows us, comparing to the previous approach, it doesn't block the whole thread and doesn't wait until one of the client is ready. It just answers us. If there is nothing to process, it simply returns an error. And that is good because we could spend, the routine could spend time on doing more important things like listening for other sockets or processing CPU important tasks like, I don't know, sorting algorithms. And the last but not least is using non-blocking asynchronous input-output. It is represented by a family of AI or system calls. But the problem with that, the programming complexity increases. And the programmers from Node.js could tell you that it's not that easy to understand the state of the application in a certain amount of time, in a certain point of time. So that is a good approach, but comparing to the rest, to the previous approaches, the best one of them is non-blocking synchronous I/O. It's not surprisingly that actually this approach is used in a Go language. But I want to say another thing about the Go. Go runtime library allows you to run the Go routines in parallel. Comparing to again to Node.js, where you can't use efficiently multiple threads, where you can't run parallel algorithm really in parallel. Go resolves that problem. It allows you to use multiple cores of your multi-core processor. It allows you to utilize all of the resources of the CPU. And comparing to the benchmarks, sorry for being so lazy. I didn't want to do it by myself, so I just copied the data from the internet. And according to the multiple benchmarks made by different guys from the internet, the efficiency of the Go language, which is using the parallel algorithm in the processing of the client connections, is better than in Node.js. Let's see how the concurrent server could be implemented in the Go language. You've probably also seen that approach. This is the most simple one. So we're just creating a new Go routine for each client connection and serving in a separate Go routine. And the same for handling each request of the client. You are going to serve it in a separate Go routine as well. If I will write something like that, where the client, the program simply creates some amount of client connections, for instance, 1 million, and only writes one word and would like to receive the response. If you noticed before, that our program simply translates the request to the uppercase and returns it to the client. So that is what our client just wants. It wants to translate a simple word and get it in the uppercase. But testing that within an environment limited by the memory, we are quickly get acknowledged that that approach doesn't work, and our server is simply killed by the Linux kernel, or precisely by the out-of-memory killer. What is happening? The answer is simple. Every Go routine you spawn requires at least 2 kilobytes of the memory. And, well, that is a problem. If we would like to handle 1 million connections at once, we will need at least 2 terabytes of memory, which is much more than the 256 megabytes we've allocated for our program. But we actually don't want to do that. We would like to handle as much as possible. And to do this, we could make a worker pool of Go routines. So that approach comes from the pre-forking approach, where we spawn multiple Go routines before the actual processing. And instead of running each new process in a separate Go routine, we simply assign a function to our pool and make it define how it will be processed. And this actually works well and allows us to eventually handle the 1 million connections. Not at once, but eventually. But the painful reality is that approach, as I showed you before and claimed bad approach, is a working pattern in a standard library. Either HTTP, net HTTP, and XNet HTTP2 brand new library is lack of this simple solution, which leads to the consequences where all of your applications are dead when the load on the server increases. So what are the conclusions? Go uses non-blocking asynchronous input-output for multiplexing the client connections in a single thread. And this is one of the best approaches available. Apart of that, Go efficiently utilizes the CPU of your server, efficiently utilizes the resources available on that. And Go language is a very good framework of doing things right. So thank you very much for listening to me. What else are your questions?
If you have a question, please raise a hand and we will get you a micro.
Hi, thank you for your job, for all dude. I have one question. So in real life, nobody writes servers that writes hello world or do mice like 2+2. In real life, we have a serious counting on the servers, a serious operation like calls to databases and etc. And have you measured the performance of single core server on the Go with a lot of calls to databases and with like these asynchronous parallel servers?
No, I did not. It's a question.
Okay, so are you 100% sure that this parallelism will gain us a lot of performance comparing to all single server?
Excuse me?
Are you 100% sure that parallelism on, for example, 8 cores or 16 cores in a Go will gain us a really boost in performance?
No, definitely
comparing
not.
with
If you are talking about only input-output, it definitely wouldn't improve your program much. And instead, if you have algorithm like, I don't know, some computations or image compression, for example, if your server would like to for compressing the images, the CPU or parallelism makes your task faster.
Yeah, you say that parallelism in compressing images, you mean inside the server? So we have a lot of calls to compress images, and it will do faster?
Definitely.
Why? Because if you, for example, if you have 1 million RPS, and you will get, for example, 1 or 10,000 requests per second, and it will create a lot of Go routines, a lot of parallel threads, and you will out of memory and out of CPU, so all the other requests will gone with timeouts and will die.
Well, that's actually what my talk was about. And well, there is no task for processing all of the connections, but handling as much as possible. There is no need to say, okay, if we won't handle all of them, then we shouldn't handle all of them. We handle as much as possible, right?
Yeah. Okay, thank you.
Thank you very much.
Hello, my name is Max. Thank you for your historical overview of high concurrency problem solving. And my question is, as far as I remember, on one of the last slides, you mentioned that neither HTTP package nor HTTP2 doesn't allow to set handler's limit, right?
Right.
And on the next slide, you said that Go is a language for writing high-performance servers.
Okay.
So I see some contradiction here.
Why?
So
The standard library is not a whole language. As long as there are alternatives for the standard HTTP server, there is a fast HTTP server which actually allows you to set that handler limit. But the Go language itself is still a high performance.
okay, so you're suggesting to use some libraries outside the core packages in order to meet these problems, right?
Well, probably if you, I probably would like to say that there is a problem, and it problem requires some solution. And if we are smart enough to do this right now, that's probably should be done right now.
Okay, I got you. And the second question, don't you think that in real life you almost never can handle all your requests with one application, and almost always you have some kind of load balancer, and maybe it's in zone of responsibility of the balancer to limit the amount of requests going to one backend, and maybe we shouldn't have it in the level of application.
Yes, definitely it's one of the best approaches to just put a load balancer in front of your server applications to balance the load and to make to assign less load on the server itself. So I 100% agree with you.
Okay, thank you.
Thanks.
Thank you for your wonderful presentation. I have a question. You said that the synchronous non-blocking calls, system calls, are better than asynchronous non-blocking system calls, and I didn't quite understand why it's like that. Could you explain that, please?
Well, it's very subjective, but as I could say, the complexity of writing asynchronous applications is higher than writing the applications in natural blocking approach, in that natural blocking way. It's just simpler to find guys that understand how the flow of the applications goes one by one than finding the guys who understand how asynchronous code works. It's the matter of the practice, probably.
And Go routines doesn't help in this case.
Well, why?
Because in Go routines you have synchronous code, but it's kind of asynchronous.
Well,
or it's not a sphere of Go.
Well, I believe that anyway, using the imperative approach of the Go language, you could write better understandable programs than using a callback approach. That's probably my subjective opinion on that.
Okay, thank you.
Thanks.
Yep. Thank you for your talk. My question, maybe you can name or explain several examples how you use concurrency in Juno, some patterns, interesting cases.
Well, it will be another presentation.
Okay, maybe some, yes.
Anybody else?
Yeah, any more questions? Come on, we still have time for questions. Okay, fine. So, Yasha, thank you very much.
Thank you.
No, we have someone. Yeah.
What can you tell about difference in performance between channels and mutexes? Like, how do you synchronize your Go routines or threads or whatever, and which way do you prefer?
In a Juno, you mean?
Yes, for example.
Well, usually it's really defined by the practical reasons of using channels and mutexes. Sometimes it's just simpler to write mutex, despite of the channel more efficient. So sometimes we prefer the mutexes over the channels, because the programmers that are working here came from the different languages where there are no channels, and they tend to use the approaches that they familiar with.
Okay.
So
More questions? No? Yep.
Anybody else wants a ticket?
Have you any problems with choosing some libraries for database to be good in performance?
Sorry, I don't hear anything.
Have you any problems with choosing libraries for databases or to be good in performance? For example, PostgreSQL or MongoDB, what we use.
Oh, I believe there are wrappers for the standard for the open source libraries, but I don't think they're used to improve performance. Probably they are used to make the code of our microservices more generic. Probably some of them just provide us ability to create a pool of the connections, but I don't think that they somehow increase performance of communication with Postgres and Mongo.
Thank you.
Thank you, Yasha. And thank you, everyone who had questions. Let me remind you that we have a T-shirt, GoWay T-shirt campaign as well. And Yasha, can you please select the person who, to your opinion, asked the most interesting question, and he will get, or he actually it was, a T-shirt.
Sure. So there is a guy in a blue T-shirt and glasses, so I believe that asked me about the load balancers. So probably he deserves that.
Okay, and what about Juno ticket?
Do you mean I should give it to the different persons?
I don't know, it's up to you.
Okay. So then to the first guy that asked me about the real-world applications, he gets a T-shirt, and Max gets the ticket to the High Load++.
Yeah, come on.